Alright, let's talk about inverse transform method. Now, why do we even care about this method? What does it do for us? Well, as I had kind of mentioned in some of the previous videos, we need distributions. And distributions on paper don't always look that neat, and they do not always make that much sense. But when it comes to graphs, it's an easy way to actually see what's going on. I'll try to include a few graphs at the end of this video so you can see what I'm talking about. So, for here, let's think about what inverse transform method does. It's able to help us give a distribution table. For example, remember we had those percentages and everything? Well, in order to develop that kind of idea, this is very helpful, especially if you have an idea that one thing, the issue with the simulation before is that everything's linear. Maybe you don't have a linear model. Maybe as time goes on, price you can charge goes down or something. Who knows? So, with this method, you have a function and you integrate it, and that's kind of like your CDF or PDF. Usually, this is a piecewise function, so you have to split it into parts. You integrate it, and then you set that integrated function equal to a random number r. You've generated that random number r based off of that Monte Carlo sampling technique we've already been doing, and you'll continue to do that for future things like this. Well, then you set this integrated function equal to r, and you try to solve for x if possible. Sometimes it will not be possible, and in that case, either you, 1, drop it, 2, make a case-by-case scenario, for example, when equal to this, then this number. We may run into that in this problem. But what you get is your new random variate. So it's kind of like a more complicated way of producing random numbers. So you produce random numbers with the Monte Carlo sampling technique. You use your inverse transform and you plug in your random number into it and then see what number gets produced. So it's sort of like an extra step to guarantee a little bit more randomness, but also guided randomness, and that's the really big key here. So in our example, we have f of x equals half when x is between 0 and 1, and we have f of x is 3/4 minus x over 4 when x is between 1 and 3. You'll notice that it includes 1 in 2 of the problems, and this is just something that was in the problem, and this is something common. You'll find that it will seem weird because it looks like it can kind of fit both. I've got no answer for you there, it's just something I've noticed. So, because this is a piecewise function, I've split it up into two separate sort of sub-functions. You have f sub 1 of x equals half, and f sub 2 of x equals 3/4 minus x quarter. The idea behind that is that's easier to integrate in, since we have to integrate this piecewise function. So, we take the ranges, but we actually do it half and half sort of thing. So because x is between 0 and 1, we have to integrate first between 0 to x, and then next from x to 1. And we're going to have to end up integrating 4 times here. So the first example, integrate at half, easy enough to do. You get x over 2, and you go from x to 0. The only thing that matters is the x. 0 is going to drop, so you have x over 2. Awesome. Do you end there? Not quite. You're going to say x is equal to 2r, because you need to solve for x. So x over 2 is equal to r, because r equals this function. So yeah, you just solve for x. Alright, you found out part of the function when 0 is less than or equal to r, which is less than or equal to x. Cool. Now, and you'll know what x is because you'll know what r is. It's kind of like the computer is able to handle it quite easily. So next up you have r is equal to, and by the way, this r is the same on all of these, interestingly enough, but r is equal to integral from 1 to x of the same function. You get the same result, except this time you're going from 1 to x, so you have half minus x over 2. Now when you solve for x, you're going to find that x equals negative 2r plus 1. And I think you can kind of picture the idea that for part of a graph, you've got a line going up, and then for the other part of the graph, you've got a line that's going down. But interestingly enough, it is going down probably like this, not perfectly. Like I say, I'll try to have a graph, show you examples of things. So there can be weird gaps in these graphs. It can be weird, but it works. So, the next one, f sub 2 of x. we're going to go integrating from 1 to x. That's going to give you 3/4 x minus x squared over 8. And you have to plug in from x to 1. You're going to get negative x squared over 8 plus 3x over 4 minus 3/4 plus 1/8. I didn't add them up, but you can go for it. When 1 is less than r, which is less than or equal to x. So it's kind of like r has to be between 1 and x, somewhere in there. That's going to give you this crazy complicated equation. There are ways to make it so that you can kind of set it equal to x. The trouble is, though, with a quadratic function, this is where you run into some trouble. And this is where this problem, I really wish they had given a different one, where you could do it, but here we probably could through some craziness. I'm not sure how. I think you could probably easy enough solve for case-by-case scenario. So if you solve for like when r is equal to 0, for example, you might be able to have specific cases for x, and that's fine. That's something you can still plug into a computer. Moving down here, you have same kind of thing, except your range is from x to 3, and so you get the same result, except now you're going to have 9/4 minus 9/8 minus 3/4 on x plus x squared over 8 when x is less than r, which is less than or equal to 3. So in the end result, you're going to have a graph, and you're going to have 4 different line types on this graph. 2 of them are going to be linear, 2 of them are probably going to be quadratic, is my best guess. And why would you want this? Well, maybe you have a time series sort of thing where maybe you have 5 minutes to place an order, and for some reason your company has decided, all right, we're going to charge different amounts based off of how long the customer has had to wait for. So in the first minute, they're fine, it's normal pricing. If they get it really quickly, they pay the same amount, and as time goes on, they have to pay less. But then as you go into the second minute, for some reason that goes back down. But then over here with the quadratics, in the 3rd to 5th minutes, it just goes all over the place. It might not make sense with a food example, but it might be better to use this with something like weather. Although weather is a bit too chaotic, and this isn't really good for a chaotic model. It's a specialized case-by-case scenario, and you will need it if you're going to go into simulation for sure. The other method is acceptance rejection method. That's a little bit more complicated because it's not exactly so much of a math technique as it is just a way of telling which random number to use. And that's the same thing as this, keep in mind. That's all this is really doing. It seems complicated, but what it's really doing is saying, all right, we've generated a random number, but we need to guide it so that random number had a probability. But what is that probability? And maybe your probability isn't just something that's linear. And I think this is an example of a continuous system. Not sure about that. But in that case, you're going to need something a little bit more specialized. You're going to need to have different distributions and such. So that's what this is all about. But obviously a really big issue is when you come into contact with something where you can't easily solve for x. That becomes a really big issue. And that's when this method starts to fall flat. And it's why you might want to use the acceptance rejections method. But it kind of falls flat too. And anything beyond it isn't covered in Winston. So this is kind of where we stop in Winston. He kind of covers the acceptance rejection method, but not in too much detail. If you want to solve more problems like this, you can go to the book. If you want to learn more about acceptance rejection method, feel free to go to the book. I think I'm just going to end it here though, because acceptance rejection method is more of a computer technique than something we would do ourselves. And without computers, we're a bit limited on what we can do. Regardless, if you want to solve more problems to try to give more examples, feel free to let me know in the comments, and let me know if there's anything you'd like changed or anything at all. Thanks for watching.